There we are. Yeah. Hi, good morning, everyone, and thanks a lot for the nice introduction and also for the invitation to give a keynote in this conference. Today, I'll be talking about cross-layer optimization for embedded machine learning. Before that, perhaps a quick introduction about myself a little bit. So I got my bachelor's in computer engineering from NUS Singapore 2002, and I did a joint master's between NUS and TU Eindhoven from the Netherlands, following a PhD, which I finished in 2009. And I then spent about 6 years as a faculty member at NUS, and thereafter I joined TU Dresden since 2015. Besides teaching and research, which I love, I also like gliding, which is flying actually quite a lot, playing violin and dancing salsa once in a while. So in our chair at TU Dresden, we currently have 8 PhD students funded by many grants, plus 3 external from Bosch, Global Foundries, and Infineon. We also have 3 postdocs, and in addition to these 2 groups of people, we also have regularly interns and thesis students from India and other places, also from IT Indore, actually, quite a few of them. And we are working on various topics. One of the topics we are working on is designing for beyond CMOS circuits. As you all know, Moore's law is driving the power and area quite a lot, actually, and therefore we need to go to beyond CMOS architectures to design some novel circuitries. We're also working a lot on approximate computing. I'll talk a bit about that today, and also a lot on neural network design and optimization. Besides these 3 applications, we're also looking at cross-layer reliability. As we are going towards smaller and smaller transistor sizes, they are becoming more and more unreliable and they are more prone to errors. So how do you deal with such problems? How do you make a reliable circuit? And again, we have cross-layer concept over there, which I'll briefly introduce today. And lastly, we are looking at how to use FPGAs to accelerate various applications, and in particular, partial reconfiguration on FPGAs, which means you can change a part of the circuitry at runtime without disturbing the other parts of the circuit. So today,
Akash, I just wanted to say hello and welcome. I was muted, so I couldn't say earlier. Yeah, please go ahead. Yeah.
Sure. Thanks a lot for the invitation. So today I'll first talk about the neural networks or machine learning in general, what they are and how they really function, followed by what is approximation, why do we need it, and how does it really work. And towards the end of the second half, let's say I'll talk about the cross-layer optimization, the main theme of the talk. How can we realize these machine learning applications on embedded platforms? And there we look at aspects of circuit, architecture, and application level. Yeah. So I'm sure you all know what the applications of machine learning or artificial neural networks are. And one of the most common examples is Alexa or Google or Siri. Right? So at my home, for example, I already have 6 Alexa devices right now. And my kids go around the whole house playing music sometimes, or just interacting with Alexa, asking what is 4 plus 4, for example, right? And if you just ask what are the applications for ANN, they are everywhere right now, right? So starting from computer vision, trying to make sense of our world around us, identifying what a photo contains, for example, to medical diagnosis, right? So in many applications, people are looking at whether they can automatically scan or analyze the scans of various parts of the body to identify if somebody has a disease, for example. So in fact, there are many works even being done right now to identify the COVID symptoms from the lung scans, for example. Autonomous vehicles is another major application. I'm sure you have all heard of Tesla, autonomous driving cars. It's especially very popular in Europe and Americas. And the entire idea over there is to use machine learning algorithms to make sense of the world around them, using production line robotics, and like I said, natural language processing, for example, Siri. These are huge applications of artificial neural networks. And what makes them really suitable for multiple applications is that they can model non-linear relationships, which is very hard to do with conventional approaches. Right? So I would like to show a small video of the Tesla S model of the autonomous driving, and the system actually has various radar and cameras, and they identify the objects like cars, pedestrian, traffic signs, etc. So this, for example, is a video from the Tesla website. Actually, you can see there are like internally 3 different cameras being used for processing, which you can see over here. And all these objects are identified with blue and the green rectangles over here. And you can see how fast the processing has to happen to make sense in real time of the multiple video streams coming over there, identify all the objects, and to see if any of these objects can be a threat to the car or the car can be a threat to the object itself. So there's a lot of processing going on actually over there. And Tesla's actually have now produced their own custom ASIC, custom chips to actually do all the processing. And until about a year ago, they used NVIDIA GPUs to do all the complex processing involved in real time. So I'm sure you all know, but just a quick recap for those who you may not be aware. Machine learning are basically a class of self-learning algorithms, right? And you train them by supplying a huge amount of data, right? And then you test them with other data set to identify if your training has been good or not. And the basic idea for machine learning is to use brain-inspired computing using neurons and synapses as what we have in human brain as well. And deep neural network, in contrast with regular machine learning, actually refers to deep because it has many learning layers, even like 50 to 100 to even 1,000 in some complex networks. And what is unique about these deep neural networks in particular is their high classification accuracy. They're able to predict very accurately what they are trying to make sense of. Right? So in fact, they are so accurate that there's an ImageNet competition where they identify the top 5 errors shown when you have an image classification involved. And in 2015, the deep learning algorithms outdid human accuracy even, right? So traditionally, if you look at the algorithms until 2011 or something like that, they had roughly 1/4 of the results, roughly, let's say you can say wrong, right? Since 2012, the rate of accuracy has been really improving, so errors have been decreasing. And about 5 years ago, they outdid the human classification. So if you put a human over there to identify if this is a cat or a dog and the image is really bad, but the machines would do better than humans in most cases nowadays. So artificial intelligence has been around for a long time, since 1950s. Actually, there have been papers or algorithms published in this particular area, but they did not pick up very much actually. And the bulk of the reason for that was lack of the hardware platform to enable that, right? So since 1980s, we have used the spam filters, etc., which is also based on machine learning, but again, only a little bit. But since 2010, or let's say the last decade or so, we have seen a huge growth in machine learning or artificial neural networks, in particular because of the hardware being able to provide the computational requirements that these complex algorithms have. And also because of data centers, which are able to now provide multiple or as complex systems as you want in practice. So these are inspired by our brain, of course, right? And the basic computational element of our brain is a neuron. And this is how it roughly looks like. Let's say you have a nucleus over here, where these dendrites obtain the input from multiple other neurons, let's say. And depending on the value over here, these axons carry the impulse generated by this particular neuron onto the other parts of the, or let's say the other neurons afterwards, right? And we have, of course, a huge number of neurons and synapses which can connect multiple neurons to each other, right? So similarly, what is done in an artificial neuron is you essentially model a particular neuron, let's say a cell, and the connection from different parts of the, or different neurons over here are also modeled as a synapse with a multiplication over here. So the x0, let's say, indicates the value coming from a neuron, and depending on how strongly the overlap between two neurons is, you get a weight function over here. So if the match is perfect, you get perhaps weight of 1. If it's very bad, you get a weight of 0, for example, right? So depending on the multiple neurons over here, you basically add all the inputs coming from various directions of the same neuron over here. And depending on the value which you have in the end, you determine whether you should produce a response to the output or not. Yeah, this is roughly an idea of how an artificial neuron looks like. And when you have multiple of these together, you essentially get an artificial neural network. So this is what we call as a layer in the middle. Here you have the inputs, which in real world would be your eyes providing input to your brain, for example. And here's an output layer, which then makes sense of what your eyes are actually looking at, for example, or your ears are hearing for that matter. And in a deep neural network, as I mentioned, you don't have 1 or 2, but sometimes even 1,000 layers, depending on what you are trying to make sense of in the real world. So typically, if you, let's say, have an image which you're trying to make sense of, in the beginning, you will have some kind of low-level feature identification. Then you have some kind of mid-level and eventually the high-level features, right? And all through these layers, you have fairly complex algorithms. A lot of computations are involved over there, lots of multiplications and additions in particular. So this is an example of a lean 5 network, which the idea is, which actually is used to identify optical character recognition. So whenever a human writes something, for example, to make sense of the handwritten letters, right? And this 32 by 32, which is a small pixelated image, let's say, and there are many layers over here, many layers like average pooling, subsampling, convolutional, fully connected layer, etc., etc. So all in total, this is a very old work of 20 years old, this particular network actually, and even in that old work, there are about 60,000 weights to be stored and 340,000 roughly multiplication and accumulate operations to be done per input picture. Now, when we look at the complexity of the popular networks, it's unimaginable, right? So even smaller networks, so all these networks which you see over here, AlexNet to ResNet, for example, are really operating on fairly small images of 224 by 224 pixels. Right? Compare that to a full HD camera that you have nowadays mounted in most of the autonomous cars already. And even in these smallish, let's say, networks, you already have up to 50 layers, for example. And the total number of operations we're looking at is about 4 billion operations for a single image inference, not even training, right? And the number of weights which have to be stored is also huge, right? So you're storing 25 million weights. So if each weight is a 4 byte floating point number, for example, you're looking at 100 megabytes of data just for the weights which have to be always being stored. And looking at again 4 billion operations per image inference of such a small size. If you have full HD, you will have roughly about 30 times more computations per inference. Right? So realizing this takes a big toll on your computational hardware. And that's why if you look at the modern hardware which is being used for machine learning, typically it is run on high-end servers, right? So I have broken this down into training and inference. So in inference, for training part is done typically in huge data centers where we use GPUs, TPUs, or NVIDIA Pascal, again, GPUs over here, right? What we also see in inference phase, again it's mostly a combination of data centers. We have Xeons, again, GPUs, custom hardware from Google, for example, and also FPGAs are used a lot in the industry to carry out this particular inference. What we also see a trend nowadays is a need or demand to do an edge or a hybrid inference. And there we have, again, a lot of FPGA and GPUs coming in over here. And also mobile chips are now coming up slowly and slowly. For example, in the Apple iPhone from Max 11 onwards, 11 Pro onwards, they have a neural processing unit inside your mobile phone itself to carry out the basic tasks of Siri and to do face recognition, etc., etc. So these are again very power-hungry, high-end devices. What should you do, or what do you need to do to enable this inference on embedded devices? Like, for example, IoT kind of platforms. If you want to make a smart sensor, a sensor, let's say, which can sense roughly how many people are in the room automatically using machine learning algorithms, what do you need to do? Yeah. And the single most important criteria in my view there is to reduce the energy consumption, right? Energy, energy, energy. We have to make energy efficient circuits, energy efficient architectures, and energy efficient application design. And I'll be focusing on these aspects today on how we can reduce the energy involved in inference in particular on these IoT kind of devices. So how do we do that, right? So the biggest problem we see is, like, for example, humans are easily able to make sense of the environment around us. We look around, we see, okay, this is a television, this is a tree, for example, this is a garden over there. Whereas computers or let's say cameras or embedded platforms or even DNA inference takes a lot of requirement for these kind of purposes. And why is that so, right? So if you look at this particular graphic, it's taken from IBM Watson playing Jeopardy, not quite Alexa, but let's say the initial approaches which could do natural language processing and give an answer to a certain question. So in Jeopardy, for example, if you ask a particular question, let's say this IBM, Watson is winning with $77,000, whereas humans are lagging behind at about $24,000, $21,000. Right? So you would say, well, IBM Watson is doing pretty good. It has almost 3 to 4 times the money it has earned. But the question is, at what cost? Right? So if you look at the power consumption of a human brain, typically a body operates at about 20 watts of power, not more than that, right? Whereas an IBM Watson consumes about 200 kilowatts. So we're looking at a factor, an order of magnitude 4 more power required to increase only about 3.5 to 4 times the money which is being earned in this particular game. So the question comes, is it worth it, first of all? And secondly, why are we humans so much better than, let's say, this kind of computer at this particular application, right? And the reason lies in the fact that humans approximate. Right? So if I ask you in the audience over here, is 923 by 21 more than 1.75? I think it's a fairly easy answer. My 8-year-old son could probably answer, yes, it's true. It is more than 1.75. If we make it slightly more complex, and I ask you, is it more than 45? It will take us probably somewhat more time. People who have seen, perhaps you could do cross multiplication over here and identify, okay, I can maybe multiply these two numbers over here. And then I know this two is 945. So this is actually smaller than 945. So answer is no. Slightly more complex, but can be done. Now, if I ask you, what is the exact number of 923 by 21 in decimal? We probably will take out a pen and paper and start working it out now, right? Or use a calculator, for example. So the point over here is that we human beings, depending on the accuracy required of the application, we increase our effort accordingly. Right? So very simple tasks require less energy, less effort. And as the tasks get more complex, we spend more energy on them. So the application context dictates how much effort should I put in, because I know what is the amount of accuracy required for this particular application, right? But a computer, on the other hand, doesn't do that. Right? So if you just ask, the computer, if this is more than 45, the answer is no. If I ask if it's more than 1.75, the answer is yes, it is. But a computer worked very hard, much harder than necessary, because underlying algorithm for both of these is actually the same. Yeah, x by y to a floating point division over here, essentially. Right. So the accuracy which is nowadays provided in the modern computers is usually an overkill for many applications, leads to inefficiency. And now the question comes, can we make these computer systems more efficient by providing just good enough results? And that's the bottom line of how we can also use it in approximate computing and deep learning algorithms. So most of these deep learning algorithms deal with typically noisy real world. Right? So if you have to make sense of the world around, let's say with a camera, the camera sensor is not very, very accurate. Right? You're making sense out of the world, which is anyhow noisy inputs coming in the system. Often the input data has huge redundancy as well, especially in terms of making sense of video streams. So multiple video streams which are being taken by a Tesla camera, for example, they will see 80% of the frame being the same. Yeah, so there's a huge overlap over there and very new part coming in there. Further, many applications, so as a human being, we have perceptual limitation, right? So many applications, let's say, which decode into full 4 or quad HD resolutions, our eyes can't really make out if the blue color is slightly off in one of those pixels. Yeah? So do we really need to spend so much energy and effort trying to decode those frames, right? So these are, I won't go through all of them because of time, but the basic idea is that many of these applications have this intrinsic resilience built into them. And what we will look at in this presentation is how we can actually bring this resilience all the way down to the circuit level to make more efficient computing. Yeah. So like I said, in most DNL applications of cognition, mining, and synthesis, and research shows that we have about 83% of runtime spent in computation which can be approximated. Right? So there's huge potential of approximation in these kinds of applications. So if you look at applications like searching, again, machine learning algorithms are making sense around the world, most of these either don't have a golden answer, or because of the perceptual limitations, or because of working with noisy data, it's not possible to always give a correct answer, right? But on the bottom side, from the hardware perspective, we always aim to provide strict numerical or Boolean equivalence, assuming that whatever inputs are coming in are perfectly accurate, and we need to have every single output always correct, right? So the question of approximate computing, or the paradigm of approximate computing, relies on the fact that we bring this approximation down from the application through the processing stack which we have, not only in the application level, but also in the architecture, logic, and service level. Yeah. And what we also see actually is it works very well nowadays, in particular, because if you look at the devices becoming smaller and smaller from, let's say, 16 nanometers to 10 nanometers and beyond, we are seeing that it becomes more and more challenging to provide the right level of accuracy results which we could guarantee in the past. Now, to provide the same level of correctness in the circuit level, we have to do much more error correction. We have to cut more corners over there and provide more guarding, let's say, in the hardware context. And therefore, when we're able to relax these constraints over here, we're able to provide much more efficient circuits in terms of computing. So I'll first start with approximate circuits. Right. So I will basically go through some of the works we have done in each of these areas. I won't be going through an exhaustive list because of time, but if you have questions, I'll be happy to answer some of them afterwards. So one of the works I'll talk about today is what we call SIMDive, where we proposed SIMD. SIMD, as you may all know, is single instruction, multiple data. The idea is that you have the same instruction coming, which you operate on multiple data streams. So for example, if you're looking at a whole image decoding, where you have to perform the same operation for every single pixel, it's an example of single instruction, multiple data. You can have hardware where you supply only the instruction once and the data multiple times, and then you get the answer, let's say, a bit faster. So in this particular work, we designed a multiplier and divider, approximate multiplier and divider for FPGAs with tunable accuracy. And for this particular purpose, we used what we call Michel's algorithm. Now, Michel's algorithm actually relies on basic idea of multiplication, where you can convert the operands into their log form, you do addition, and then you do anti-log to get back the answer, right? And similarly, if you want to do division now, you can do the log operation and do a subtraction, and then do an anti-log, you get the answer. Now, any of you, I'm sure, who has tried to actually use the log tables in the past and then get the answer of big numbers will know it's inherently not very, very accurate, right? Because when you do the log conversion, you lose some accuracy. When you do anti-log, you again lose some accuracy. But the good thing is, now your multiplication is broken down into a simpler add operation, especially for division, into simply a subtraction operation. And that leads to huge area and power savings. And in our particular work, even for finding the log operation, we use what we call leading one detection, right? And that basically allows us to identify what is the log value in a faster and compact way, right? So you identify which is the leading one, you align the fraction part, you add the integer and fraction part separately, apply some error correction, yeah, and then you do the anti-log after that. And that gives you your multiplier or divider result in the end. So in this particular work, we basically proposed the very first integrated multiplier and divider architecture in the same hardware, which has much more improved latency and error tunability. Overall, if you compare with the 32-bit divider, we have 37 times more throughput. So it's a huge improvement. 37 times is almost 2 orders of magnitude, with very little overhead to support SIMD in the overall system. So SIMD means that from 32-bit, you could choose to have either 8-bit, 16-bit, or 32-bit at runtime, depending on the application requirement. And we evaluated this approach in image processing and also in applications. So I will not go through perhaps the entire structure over here, but as you can see briefly, sorry, my boss is being strange here. Yeah. So as you can see in the first figure over here, the whole structure over here could be divided into 4 separate parts, which could be done in parallel, and it could be considered as a single 32-bit operand or 4 8-bit operands over there, right? And then over here we have a hybrid multiplier and divider over here, where it can be either an adder or a subtractor, depending on which operation we're trying to do. And finally, we have a addition or subtraction being done over here in the FPGAs. Right? So if you look at the original error in the Michel's algorithm, you get a graph which looks a bit scary in the beginning, I would admit. So for example, you have huge peaks of errors over here. And if you look at the top view, it looks something like this actually. And this is for the division part. So what we do is we actually divide this entire error space into 64 parts, 8 for the operand A and 8 for the operand B, for example, looking at the 3 MSBs over here. And as a result of that, we store all the possible error. We find the mean of each of the area, for example, over here, and we calculate the average error, which we then correct the answer with. And as a result of that, basically, the initial error which you see on the left side now becomes what we see on the right side. So all these huge red parts over here, which are the peaks of error, are reduced to very small blue parts over here. So this is basically what happens when you apply our error correction technique. And if we see numbers, for example, over here, as compared to the original Michel's algorithm, the average error is about 4%, while we get about 0.8% only. And the peak error from 11 to about 5%. In the end, we get roughly about 37 times higher throughput, like I mentioned earlier. Looking at the high-level application part over here, we try to, here we show the results of image blending and the Gaussian noise smoothing algorithm. And we see that the original result with the accurate multiplier and divider gives you this particular image. On the second one over here, by applying our SIMDive approach, you get the third image over here. It's hardly possible to make out any difference in these two images, and similarly in these two bottom for the Gaussian noise smoothing filter. In terms of the ANN testing, we applied this algorithm with fashion and the MNIST handwritten approach. And what we see is that when we use double precision floating point, which is 64-bit accuracy, let's say you get over here 97.09% accuracy in the digit data set, whereas the SIMDive we get 96.67. So it's hardly 0.4% drop by using only 8-bit approach, and even that to approximate. So you really get huge amounts of gain by doing this approximation with a very, very small 0.4% loss in most of these algorithms over here. Yeah. I'll go briefly about approximate architecture, but not too much because of time. So in approximate architecture level, we are currently working on a project called REAP, which stands for Reconfigurable Approximation, where the idea is that you can reconfigure the level of approximation desired at runtime. So at runtime, if your application says my images are very clean, or I don't really care about the accuracy too much, if you give me 50% accurate result, it is good enough for me. Right? But there could be times when it says, no, I want to have 95% accuracy. So then our algorithm can basically customize the architecture accordingly. So the way the whole flow works is split into two parts, design time and runtime. At design time, we create a library of approximate logic blocks, adders, multipliers, and we characterize them for the error distribution, the power, the area, performance, etc. And we store them all in a database of Pareto optimal hardware design. At runtime, depending on the application requirements and which applications are actually in operation at the moment, we have a runtime manager which reconfigures this particular hardware platform, let's say, with the desired components with the desired accuracy. Right? So this is an example of, let's say you have an MJPEG application running in the system on the left side, and because we have enough hardware available, we're able to run all the components at 100% accuracy over here. Now, sometime later, there's another application, let's say, Susan application, which also comes in the picture. And then we have to still fit both applications in the hardware. So what we do is we shrink the accuracy, we reduce accuracy of some of these components to ensure that both applications can be run without any problems at runtime and still meet the accuracy requirements of the application. So this is basically the idea of an architecture level approximation which can be done. Yeah. Lastly, I look at the application level approximation, and some of these slides that I will present today were actually done in collaboration with Dr. Kapil Ahuja's group in IIT Indore. In general, the DNN optimization can be broken down into three parts: pruning, quantization, and weight clustering. Pruning essentially refers to making the network a bit smaller by doing away with some of the required connections in your architecture, in your algorithm. Right? Quantization, on the other hand, which I focus mostly on this aspect, is trying to reduce the amount of precision which is needed for the weights and the data which is coming in the system. And it allows us to reduce the overall memory usage, because now let's say instead of 32-bit floating point number, you can manage with only 8-bit number, for example. And in the end, you are able to then do away with very complex hardware. So you have very simple hardware, and you also have less memory requirement, because now you only need 8 bits instead of 32 bits for every single operation, right? And some of the common operands which are used in this literature are integer, 8-bit, 16-bit, or even floating point 16-bit, actually. So in this particular work, we will skip these slides. In this particular work, we propose a new kind of quantization approach, which is much better than an 8-bit integer or 8-bit what we call linear quantization approach, actually. So the way this particular approach works is we identify the leading one location. So let's say you have 8 bits of your quantized value. You look at the 4 bits will store basically where the leading one, the first one, is present in the weights. And the remaining locations over here are then used, let's say in this case 3 bits, because we have a sign bit over here, to store the value which follows the first one which you have stored. Okay. And we had a variation of this particular scheme called a line scheme, published in Access this year actually, where we merged away this boundary. Rather than having fixed 4 bits and 3 bits over here for 8 bits or more for the other bits, actually, we make this boundary flexible over here. So depending on individual layer, depending on the weights distribution of the individual layer, we identify what should be the right number of bits to store for the leading one and for the other values after that. And we realize that this particular approach works extremely well and gives very good results. So I have some of them to show you. So this is from a convolutional 1-1. For example, the histogram over here basically shows you where the leading one is present in your weights. So we see that most of the leading ones are around 3rd to 4th location, for example, 2nd to 4th location. The same thing happens also in the bias method. And similarly for some other layer, for example. Okay. Now, maybe I'll skip through these slides actually. What we see in this particular work is very interesting is that the error values, depending on which algorithm you apply, can really vary a lot. So for example, our align, the most recent work that I explained earlier in the previous slide, this part over here has the least amount of error for almost all the layers actually. The log to lead, which was earlier, which is a fixed number of bits used for each layer, you actually have slightly larger error than the align approach. Now that's about the error in terms of numbers. How does it really perform with, let's say, neural network applications? So what we did was we used the ImageNet database to identify the classification accuracy of our approach. So if we use float 32, which is considered as a golden standard because everybody uses float 32 in most of the software implementations, the top 5 accuracy is 85.74. Our align approach is able to provide 85.71. That means 0.03% variation in terms of accuracy, which is hardly anything, right? Again, with the concept of going, there is not always a golden answer, right? In that sense. So it's a very, very small decrease, but what you're able to save is already 1/4 of your memory, because instead of 32 bits now, you only have 8 bits of representation. Plus, you also save in the hardware, because the hardware that you designed for this particular module is much simpler than a regular 32-bit floating point, because now you have to only do some shifting and addition to be able to realize the multiplication in a power of 2 and the following bits after that. The same thing for top 1 accuracy, it's only 0.1% lower than the float 32-bit representation. We also applied this for object detection. Here we see the float 32 result. Here we see for the 8-bit linear quantization, what is commonly used for 8-bit representation. Let's say if you would use int 8, you would get the result what is shown in figure C, for example. With L2L and align, we get the bottom 2 figures. Now it's very hard to compare these 2 figures, B and C. Therefore, we have figure D to show the difference between the two. As you can see, in linear, you have quite some errors over here, right? In L2L, the errors are much better than what you have in figure D. But align almost removes all the errors. There are almost no errors at all in terms of the object itself. What you see are slight border issues in the result. but in the end, it has been able to do very good object segmentation. And as a result of that, you have saved a lot of power and energy over here. So just last couple of slides before I end. So what I explained so far were basically techniques of individual layer approximation. We explained independently the circuit level, architecture level, and the application level. What we are working on towards now, and it's actually unpublished work at the moment, is cross-layer approximation. That means to identify, to study all these three or even more if we have layers all together in synergy, and identify what would be the right mix of different approximations at different layers to give us the best result. Right? So here I have an example where we show a comparison of stride length. So stride length is basically in a convolutional operator. When you have to find the convolution of this particular image, let's say you have a 3x3 convolution, and you move in every step one to the right and one down, you basically get these 9 convolutions which you end up doing. Now, if you don't jump by only one, but let's say 2 stride lengths, so you jump by 2 over here, we obtain this this window over here, and then these 2 windows. So instead of 9, you only have 4 windows to compute your convolution for. Right? That's one of, so this is the application level approximation, because you are able to, you're modifying the way your algorithm works essentially. What you also could do is to use approximate multipliers for these convolutions. So these are 2 possible ways of approximation. And now what we do, or what we study in this cross-layer framework, is to identify how much do you gain and lose by applying these techniques. So the green curves over here, for example, show if you would use a stride length of 1 and stride length of 2, how would the PSNR, which is the peak signal to noise ratio, you could somehow take it as like a quality of end result. Right? So quality of result drops from, let's say, 16 to about 14 roughly over here by using the stride length of 2. Now, what is interesting is if you look at the energy which you spend on doing the operation has not gone down so much, from 2.9 to about 2.8. So this particular change in this particular example wasn't worth it, I would say, because although you reduce the quality of result, your energy has not really benefited much. So what we study in comparison over here is if we had used approximate hardware, so this AX1 refers to approximate with stride length of 1, you get the quality of result, which is also 14 now, but your energy consumption is reduced from 2.9 to 2.3. So you get about 25% energy savings with about 10% call return, for example, right? So by doing this, this is not the final result, it's just to motivate the idea that if you do cross-layer approximation in this particular context, you should consider what benefits does each of my approximation at each layer bring, and how can I combine these multiple approximations into a coherent approach. So we are working towards a cross-layer approximation framework where we study different degrees of freedom across the layers. We look at data by scaling, precision, software, algorithm, window size, the mode, stride length, for example, and the hardware approximation. We try to analyze the impact of each of these individual degrees of freedom in a behavioral error analysis to identify how does each of them affect the end result of my application quality. And then we do a cross-layer design space exploration to identify what mix of these approximation methods I should choose given the constraints of my application. Right? In the end, we get an Pareto front with these cross-layer approximation configurations. And that's pretty much it from me. So to conclude, we see that deep neural networks are now everywhere, and energy and computation demands for them are increasing more than ever. We want to have them the smallest sensor possible throughout the world. But to enable this ultra low energy inference, as I call, we have to have innovations across the stack, not just on one of these aspects. And therefore, we need to have a holistic cross-layer optimization approach. That's it from me. Just to conclude, most of the work that I spoke about today, we try to make open source, and you can actually go to our webpage and download some of these tools and play around in your own lab. That's it from me. If you have any questions, I'll be more than happy to answer.